Hi guys. Okay, so in this video, I'm just gonna briefly talk about coproducts. So the last video we would have seen the idea of a product, and in a product we have objects A and B, and we have our product is like has maps to A and to B. And now we're just gonna make this idea where we do the same thing we did, except all the arrows are gonna go the opposite direction. So now we have our objects. A and B are gonna be just two objects in the category. And now our objects of C, um, you know, superscript AB, the objects are gonna be objects of C, Z, and map, and we have a map from A to Z and map B to Z. Okay, and morphisms, like if I have ABX is one object and ABY is another object, a morphism is just going to be a morphism from X to Y, such that if I go from A to Y this way or this way, it's the same morphism. And if I go from B to X to Y, or just from B straight to Y, it's the same morphism. So morphisms in this new category are morphisms in the old category, but they have to kind of make these this diagram like compatible. Okay, and then a coproduct of A and B is just going to be an initial object in this category C superscript AB. We just have a little proposition that the disjoint union is going to be a coproduct of AB in the category of sets. Okay. So we need to know, so this is going to be a much sketchier proof than the one for Cartesian product, but that's okay. So suppose we have two maps, a map from A to Z and a map from B to Z. Well, there's this thing called the disjoint union. Definitely we have a map from both A and B to the disjoint union of A and B. Right? This map is like the inclusion of A into A disjoint union B, and this map is the inclusion as well. And then how do you get a map from the disjoint union of A and B to Z? How do you get that? Well, basically take whatever, so if this is F, define your new map to take whatever in A by F and take anything in B by this function, by this arrow. And then because the union is disjoint, that defines a function nicely. There's no common component of A and B, which kind of would screw everything up. Okay. So I've kind of overlooked a few things, like there's a few tricky things, like what if A and B actually had something in common? Then we need to define the disjoint union. Well, like for example, if I want to define the disjoint union of these two sets 1, 2 and 1, 2, 3, well, I just changed one of the sets slightly so that they don't intersect. Like instead of 1, 2, I just change it to be like bold 1, 2 or something, as a really silly example. And now this set and this set are disjoint because I've changed the font or something, something silly like that. And so now their union will be like a disjoint union. Okay, so there is a way to make that precise, and I mean, there's many ways to do it. Okay. But once you have the disjoint union, then you can see that you kind of have a map. You map both A and B into the disjoint union kind of by inclusion, and then that can define a function into Z by taking like your previously defined functions. Okay. Sorry if that was a little bit more sketchy. Okay, thank you.